All right, so for today's video lesson, we're going to look at our last topic of the max-min problems. These are extreme value problems in other sciences. Okay, so within sciences, maximum and minimum values are constantly being used. For example, engineers look for maximum efficiency, strength, or use, right? They want to use the most materials at the cheapest price. Also, we have biologists who study maximums and minimums concerning population growth. Okay, so like replication rates within bacteria or like viruses, right? Like what we're seeing right now. Okay, so when we are solving these problems, we're going to have two different steps. Okay, so step one, we're going to use the formulas given to create a formula in terms of the defined variable. Okay, that's step one. And then step two, we're going to determine maximum or minimum values using our derivative. All right, so let's get into our example for today. So this kind of ties into our physics 30, right? So the current in a battery is represented by the equation I is current is equal to E divided by R, big R plus little r. Okay, so E is going to be our electromotive force. So I'm just going to write this formula down. So I is equal to electromotive force divided by external resistance plus the internal resistance. Okay, E and R are and little r are characteristics of the battery and therefore are constants. So E and little r are constants. Okay, and that will make a difference when we are deriving our formula, right? Okay, so E and R are constants. The power developed in the battery is represented by the equation P is equal to external resistance multiplied by the current squared. Okay, so we know that the internal resistance of the battery, so our little r, is 0.15 ohms. Okay, so we need to find what external resistance, so what big R value what big R value will give us a maximum power. All right, so we are given two formulas here. And now I see that our current formula is already written in terms of I. So we can go ahead and substitute that into our power formula, right? Because we are looking to find the maximum power. So we want to use this formula right here, which is written in terms of power already. So let's go ahead and substitute our formula for current into our power formula, okay? So power is equal to resistance multiplied by electromotive force divided by external resistance added to internal resistance, and that is all squared. Okay, so let's simplify this a little bit. So let's distribute that that squared into this bracket. Okay, so power is equal to resistance multiplied by E squared divided by big R plus little r multiplied by big R plus little r. Okay, so this gives us a power equal to R multiplied by E squared divided by 2R squared. Or sorry, just R squared. Plus 2 big R little r plus R squared. Okay, so remember we are given in the question that the internal resistance is 0.15 ohms. So we can use that to simplify this equation a little bit. Okay, so power is equal to RE squared will just stay the same. R squared stays plus 2R times 0.15 plus 0.15 squared. Okay, so we can further simplify this. So power is equal to RE squared divided by R squared plus 0.3R plus 0.0225. Okay, so now that we have simplified this, remember that little r and E, our electromotive force, and our internal resistance are going to be constants. Okay, and remember what we are looking for in this question. We are trying to find the value of R when we have power at a maximum. Okay, so therefore we need to take the derivative of power with respect to external resistance. Okay, I'm just going to jump to the next page to continue this calculation. Okay, so we are at power is equal to RE squared divided by R squared plus 0.3 R plus 0.0225. Okay, we have a fraction here, so we need to use our quotient rule. And remember our quotient rule, y prime is equal to VU. It returns minus UV prime divided by V squared. Okay, so here U is going to be the numerator. So U is equal to RE squared. And remember that E here is a constant. So we're essentially just taking the derivative of our R there. So U prime is just going to equal E squared. Now for V, which is our denominator, is R squared plus 0.3R plus 0.0225. So V prime is going to be 2R plus 0.3. Okay, so let's put this P is equal to RE squared divided by R squared plus 0.3R plus 0.225 into the differentiated form. So we took the derivative of P with respect to resistance. And that is, I'm just going to move this down a little bit. It is the quotient rule. It takes up a little bit of space, right? Okay, so derivative of power with respect to resistance. So that is V U prime minus UV prime divided by V squared. So V is R squared plus 0.3 R plus 0.0225 multiplied by U prime, which is E squared, minus U, which is R E squared, multiplied by V prime, which is 2R plus 0.3. All of that is divided by V squared. So R squared plus 0.3 R plus 0.0225 squared. Okay, now let's distribute the E squared into our first bracket. And we'll also distribute the R squared into that other bracket. And we are going to leave this alone for now because it's going to make our lives a little bit easier. Okay, so if we distribute E squared throughout that, we will get R squared E squared plus 0.3 R E squared plus 0.0225 E squared minus 2R multiplied by RE squared is 2R squared R squared E squared minus 0.3 R E squared. Okay, I just saved a step, but those will both become negatives, right? Okay, and then again, we're just going to leave this alone on the bottom. So we still have R squared plus 0.3 R plus 0.0225 squared. Okay, so let's simplify this a little bit. So I have a negative 2 R squared E squared and a positive R squared E squared. So that will go away, and the negative 2 will become negative 1. I have positive 0.3 RE squared and a negative 0.3 RE squared. So that will cancel. And that's about it. So what we have remaining here is 0.0225 E squared minus R squared E squared divided by R squared plus 0.3 R. Oops. Got a little excited with that bracket there. Plus 0.3 R plus 0.0225 squared. So that is the derivative of power with respect to resistance. Okay, so now that we are at this point here, we've taken the derivative of our function. We need to find our critical values. So this is where the derivative of power with respect to resistance is equal to 0, right? So 0 is equal to 0.0225 E squared minus R squared E squared divided by R squared, that's in brackets, okay, so and remember, we're looking for the external resistance that will give us the maximum power, right? So we're looking to solve for our R value here. Okay, so to simplify or to solve for our r, let's multiply by r squared by our denominator to get rid of that. So r squared plus 0.3 r, 0.0225 squared. And we're going to multiply that on both sides, right? Both sides there. I just don't have enough room there, okay? But anyways, you're multiplying by 0, so those will just cancel, and we're going to be left with 0 is equal to 0.0225 e squared minus r squared e squared. Let's add r squared e squared to both sides. Those cancel. Now I have r squared e squared is equal to 0.0225 e squared. I am going to divide both sides by e squared. And last thing we need to do to solve for r, take the square root of both sides, and we will get our r value equaling positive and negative 0.15 ohms. And we cannot have a negative resistance. So our r value is equal to positive 0.15 ohms. Okay, so let's now check our answer just to confirm that we indeed did find a maximum. Now, you can take the second derivative of this function right here. Okay, if you don't want to take the quotient rule again, I understand that. Another way that we could test to find if we are increasing or decreasing is just test values to the left and right of 0.15. Okay, and we would do that again at this formula up here. Okay, so the first one I'm going to substitute in at r is equal to 0.14. Okay, so 0.0225. E is a constant, so we can just kind of leave that alone, minus 0.14 squared. And of course, that will be divided by r squared plus 0.3r plus 0.0225 squared. And this is my r equals 0.14. Okay. When you punch this into your calculator, you'll get a positive value in the numerator and a positive value in the denominator. Okay, so therefore, approaching 0.15 from the left, we are increasing. Okay, so now we can do the same thing, but on the right side. So at r is equal to 0.16, if you do the same thing as we did here, you'll get a negative divided by a positive, which is equals to a negative, which indicates that it is indeed increasing to the right of 0.15. Okay, so therefore we did find a maximum. And to answer our question, I'm just trying to find some space. When the external resistance is equal to 0.15 ohms, power is a max. All right. So kind of cool that we can have some physics cross-curricular with our calculus here, right? Yeah, so that is our only practice problem for today. So for the remainder of today's class time, I would like you to try one of these examples posted on this page here. Okay, so once you have attempted one of those and completed that, please send me an email or a text or submit it to the Google Classroom, just so I know you're completing your homework. All right. Thank you for your attention today, and I'll see you soon.